Okay, so now that we've covered inverse Laplace transforms and the forward Laplace transform of derivative functions, we can now move on to actually solving differential equations by setting them up in a linear system of equations. So, excuse me, what I want to do first is have a look at a first order differential equation, just to get the process of paths done, and then we can move on to second order differential equations. So let's have a look at this example here. So you can see that there. So if we do, say, dx by dt minus 2x equals 4, and what we'll do, we'll set the initial conditions when t equals 0, x to equal 1. So the first thing when doing this in the Laplace way is just to remind ourselves what the linear system looks like. So we know that the Laplace transform of x equals x bar. Remember, we are using our notation now to make the algebra nice and easy, where really the Laplace transform of x is going to equal the semi-infinite integral of f of t e to the minus st dt, which also we can abbreviate as f of s. All right, just to, but we're going to abbreviate that just by x bar. And f of t in this case would just be x. Yep. So, so the Laplace transform of x is x bar. The Laplace transform of the first derivative is going to be x bar minus x naught. The Laplace transform of x double dot, i.e. that's going to be the second derivative, which is actually not needed for this, but let's do it anyway, is going to be s squared x bar minus s x naught minus x1, I believe. Yeah, I think that's right. And so on and so forth. But this is all we're going to need. Laplace transform of x and Laplace transform of the first derivative. So the first thing to do here is we're just going to write down what this looks like in terms of our normal substitutions. So dx by dt is going to be x dot. So we'll just write x dot minus 2x, well, x is x, equals 4. Yep. Just move that down. Let's see. And now, what we can do is, well, is we can say the following. We know what these substitutions here, sorry, not substitutions, I'm very hard at the moment, excuse me. Right, I'm getting confused. We know the Laplace transform of these things is these things, yeah? So if we Laplace transform, say, the whole of the left-hand side, we can say that that's going to be equal to the Laplace transform of the right-hand side, yeah? So if we do the Laplace transform of x dot minus 2x, that has to equal the Laplace transform of 4, yeah? And because of the principle of linearity, we can say that that is going to be the same as the Laplace transform of x dot minus 2 times the Laplace transform of x equals the Laplace transform of 4. Yeah. So we know that the Laplace transform of x dot, we've got it up here, is this. So let's use that substitution now. So we can say s x bar minus x naught minus 2 x bar, because the Laplace transform of x is x bar, equals the Laplace transform of 4, which is 4 on s. Sorry. Yeah. But we know that x naught, remember x naught is a function when t equals 0. We know that that equals 1. Why? Because of our initial condition. So this really implies that x naught equals 1. Yeah? So let's go and substitute that in. So we can now say that s x bar minus 1 minus 2x bar equals 4 on S. Yep. So let's simplify the algebra here. X bar, S minus 2 minus 1 equals 4 on S. Now I'm going to take the 1 to the other side. So we can say that x bar, S minus 2, equals 4 on S plus S on S. Yep, so S on S is 1, so I've just taken the 1 to the other side. And now we can say that x bar, S minus 2, equals 4 plus S on S. Yeah? Now let's divide both sides by S minus 2. So we can say that x bar equals 4 plus S on S, S minus 2. Yep. Let's keep going. Now we can see that we've got x bar. Now remember, x bar is the Laplace transform of x. And the inverse Laplace transform of x bar is x. And that's what we want to find. We want to find x in terms of t. So what we really need to do is, if we find the inverse Laplace transform of x bar, then we'll have x, won't we? So if we do the inverse Laplace transform of x bar, then that will equal the inverse Laplace transform of the right-hand side. So what we need to do is find the inverse Laplace transform of 4 plus S on S minus 2. And that's why we did so much work, and that's why it is important to do so much work on inverse Laplace transforms, because this is where all the groundwork is really going to pay off, and on the partial fractions. So if we say that 4 plus S on S minus 2 is identical to A on S plus B on S minus 2. So we can say that A, S minus 2 plus B, S, is identical to 4 plus S. Yeah? So if we let S equal 2, that's going to be 0. So we're left with 2B equals 6. And that implies that B equals 3. Now let's find A. So let's set S to equal 0. So that'll be minus 2A plus 0 equals 4. And that implies A equals minus 2. Yeah? So we can say, let's go all the way back up to here. So we can say then that 4 plus S on S minus 2 is identical to minus 2 on S plus 3 on S minus 2. Okay, so now I've just got that in a nice partial fraction form. And now, if we find the inverse Laplace transform of that, that will give us the inverse Laplace transform of x bar, which will give us x, hopefully. So let's do the inverse Laplace transform of minus 2 on S plus 3 on S minus 2. And remember, that will give us the inverse Laplace transform of x bar. So remember, principle of linearity. I'm just going to write this out for full, just for clarity. So that's going to be minus 2 on S plus the inverse Laplace transform of 3 on S minus 2 equals, well, the inverse Laplace transform of x bar is going to be x. So we can see here that minus 2 on S, the inverse Laplace transform of that is going to be minus 2, yeah, because the Laplace transform of A equals A on S. Remember that? So if we have A on S, say 2 on S, the inverse Laplace transform must be just A, but in this case it's minus 2. And then plus 3. We can take the 3 out, really, so, you know, it's just 3 is just the coefficient. Another property of linearity, or I think it's something else, but anyway, it works. So you can just take the 3 out, and then it's going to be the inverse Laplace transform of 1 on S minus 2 times 3. So it's going to be 3 times the inverse Laplace transform of 1 on S minus 2. So that's e to the 2t equals x. And that's our final answer. X equals minus 2 plus 3 e to the 2t.